Okay, so first of all, let me tell you this more or less, I mean, yesterday and today uh, basically gives you the main idea of how the term's gonna continue. So we will have these interactive lecture sessions where I'm gonna write on the notepad, and I think I will also share these notes as well. But when I make these into a PDF, usually um, there is no concept of a page. So the page might be broken at arbitrary locations. So that's a bit annoying. But anyway, that's the tool I have. But still, I will share these PDF files also through MetuClass with you guys. Okay, so last time we started discussing this temperature control system. So we mainly have drawn the figure indicating all the components of the system. Okay, and then we started working our way through this diagram, and we are trying to write down. The main idea is, let me call this, you know, hold on a second. This is not what I was expecting. There are these lines and I don't know why. Let me try to switch to something else. Hold on. Let's see whether we can view all notes. Okay, so okay, this is somewhat. Is it the same? No, that's what I. Anyway, we'll see what happens. Normally, okay, so this is somewhat different than what I had from before, but I don't know why. Okay, so we have somewhat less screen area to work with, but it should be okay. All right. Okay, so what I want to kind of tell you guys is that the way we are working on this is what I call follow the signal. Okay. Okay, so what we are doing is, as you remember, we started from, in fact, the output, okay, which we called 1, which was the thermocouple device that was measuring essentially the temperature output of this process. And we started gradually writing down the equations that were involved in this system, right? We started with the sensor, the thermocouple, and the associated amplifier. So we have written B equals KB times theta, which was telling us that amplifier generates a voltage B in response to whatever small signal is coming from the thermocouple. In fact, the thermocouple itself might have an additional model, and in the laboratories you will see how that works, right? The thermocouple has a physical container, it has a certain dynamics, so the mapping from the temperature to the small voltage generated by the thermocouple is also or may also be part of the model, or a more complicated model. But here we just assume that everything is kind of combined into a single amplifier, so that in fact the temperature theta becomes a voltage B. Okay, so that's our simplified model of the sensor in this device. And then we also moved, followed the signal in a sense, and we came to the input part. And the input was composed of a potentiometer, which was allowing us to generate essentially a reference signal, R, right? Here, R is determined by where you put the potentiometer, okay? So R is a user settable voltage here, and the Kirchhoff's voltage law essentially allows us to write the error signal E as a difference between the reference signal R and the output voltage from the amplifier B. Okay, so the difference R minus B becomes our error signal, and this error signal actually is amplified through an amplifier that has a gain of Ka. Okay, this we call the second part. I call this the comparator and controller. Okay, usually this part itself, this part over here, essentially is the controller. Okay, in this case, it's a P-type controller. It's just a simple gain Ka. So the error signal is amplified and becomes V. Okay, so V is actually the output of the controller, you might say. Okay, and it drives what we will call an actuator. Okay, here, right, the solenoid valve actually is a complete package, let's say. Okay, if you go and want to buy something like this, it's going to be essentially a package that is composed of a voltage input, and essentially it has an electrical part and it has a mechanical part, and the function of this device is to set a valve position, let's call it X, in response to a voltage control input, right? This device obviously will have its own dynamics because it has a coil, it has a mechanical component inside that is moving, so there is it's an electromechanical device basically. Okay, in fact, if you want to elaborate, it's like a motor, it's like a linear motor. Okay, so now we will go so this thing is our actuator. This whole thing is our actuator, but we will have to really work out it step by step. We will start with the electrical part and we will move on to the mechanical part, and therefore we will reach what's happening with the valve. Okay, the flow of the hot steam to the boiler, to the tank. All right, so before moving on to the modeling of the electrical part, okay, do you guys have any questions at this point? Okay, so let's call 3 and let's say the electrical part of the actuator. Okay, this is basically the solenoid valve. Okay, this second name actually is something that you can go out and shop with. Okay, you can search for a solenoid valve. It's basically an electrical component that you can purchase. Okay, so what about the electrical part? So in the electrical part, okay, which I'm going to work first, basically what we have is that we have a Vs, the voltage to the solenoid valve, and there is an internal resistance R and an inductor L. If you remember in our figure, these were R and L were actually parameters of this model. Okay, so R, L are electrical parameters of the model. The mass, the friction B, and motor constant Ks are actually the we can call the mechanical parameters of this model. Okay, so here obviously there is Is, the solenoid current, Okay, so the electrical parts function is to transform the voltage. In fact, this Vs, if you remember, it is what we called V. Okay, this is the output of our controller, which is the input to the solenoid valve. Okay, so here in this electrical model, what we have is that the voltage V is being transformed into the current S. Okay, what is the underlying equation? The underlying equation, in fact, there are two of them, in fact, three of them, right? We have the topological equation, which is the Kirchhoff's voltage law. So I have, if I mark this like this, I have minus V plus VR plus VL is equal to 0 is our Kirchhoff's voltage law, okay? Voltage law. And also we have component equations for the resistor and for the inductor. So if I continue writing this, I have V is equal to R times IS, which is the current through this loop, plus L times DIS over dt. We know that the equation of an inductor is actually a differential equation. Okay. So obviously, since we are working in the Laplace domain, in order to build a block diagram, we need to transform this into the Laplace domain. So basically, my equation is that V of S is equal to R times IS of S plus LS IS of S. Okay, so which gives me the current. Since in the Laplace domain I have nothing but an algebraic equation, I can actually extract the output in terms of the input. So IS of S becomes simply a first order transfer function, R minus SL times V of S. Okay, so that becomes the electrical part of our solenoid. So that's one of our equations. And now we need to come to the mechanical part. Okay. And there is obviously a transition from the electrical to the mechanical. So let me write that over here as part of 3. It doesn't matter in which part you write it. But this transition is, as we know, as in any motor, is related with, in fact, armature controlled electrical motor, is that the current through the coil actually is transformed into a force. Okay, in the case of a rotational motor, obviously it is the torque rather than the force. So this equation needs to be written as well. So let me write it as well. Force generated by the coil, let's call this Fs. Since this is an algebraic equation already, it doesn't matter whether I am in the time domain or in the Laplace domain, but I have Fs is equal to Ks times Is is yet another equation that I need. Okay, remember I'm following the signal, right? I came from the output, I went to the comparator, I went through the amplifier, the controller, then I enter the electrical part. So the voltage becomes the current becomes the force. Now we need to determine what happens as a response to the force, because eventually we want to arrive at what's happening with the solenoid position. And then we need to arrive at the flow, how much flow. Okay. So let me move on to part 4, and I'm going to call this the mechanical part, parts of the actuator. We are still within the solenoid valve. Okay. Now, in order to do that, obviously I need to refresh my kind of knowledge on how to model mechanical systems. Now what's happening here is that I believe I'm going to also ignore the gravity. Okay, so what's going to happen is that I have a mechanical system, right? There is basically a mechanical shaft moving within a sleeve. The mass is m. Now, because of the solenoid, I generate an upward force Fs. Upward, downward, it doesn't really matter. But the nature of this solenoid is that there is also usually a spring which brings this solenoid back. Let's call this spring. So this is, let's say, recovery spring. Okay? With a spring constant K. There is mass M and there is friction in between. So there is also friction with a friction constant B. This is usually modeled as a viscous friction so that we have a linear model. Okay. Other friction models are more difficult, quite nonlinear. That's why we usually stick with the linear one. And also, this friction model is not very unrealistic because in any case where you have a lubricated motion, like in a motor shaft and so on, whenever there is lubrication, you basically have this kind of fluidic friction, okay? Or what we call a viscous friction. Now, we need a free body diagram, right? We have a mass M. Mark all the forces acting on the mass. And let's also label the direction of motion. Okay, x and x dot, let's say it is in reference to any point in the mass and is in the upward direction as a positive direction. So whatever happens, as x is increased, the spring generates a force in the opposite direction. Okay, so F spring is equal to basically K times X in the opposing direction. And also if the motion, the velocity is in the upward direction, there is also a frictional force. Let's call FB, and that is equal to B times X dot. If you remember, the viscous friction is a linearly, or it's proportional to the velocity of motion. Okay? So these are all things that you remember from 302, obviously. So what I'm going to write down is that the net force will be equal to the mass times the acceleration. Okay? Newton's second law of motion. Okay? So I'm going to use this in order to construct the next differential equation that I have. Okay? So what is the net force? The net force, F net, is equal to Fs minus K times X. These are functions of time at this point, right? Fs of t, sorry, let's do that. So Fs of t minus K times X of t minus B times X dot of t. The net force has to be equal to m times X double dot of t. This is the differential equation. Again, in order to construct my block diagram, I need to transform this into the Laplace domain. So I take the Laplace transform, in which case I have Fs of s minus K times X of s minus B times S times X of s is equal to m times s square X of s. So I have an equation in terms of the input force to this system, Fs, and the output position of the solenoid valve. Okay, So let me collect everything. ms square plus bs plus k times x of s is equal to f of s, fs of s. So that gives me a second order system model where the position of the valve is given in terms of the input force as the following transfer function times fs of s. Okay, so that's our next, the mechanical part model that we have obtained. Any questions so far? All right. Yes. Sizi çok zor duyuyorum. Bir saniye bakayım, benim yapabileceğim bir ayar var mı? Bir konuşun. Daha iyi. Buyurun. Okay. Yes. Yes, I'm listening.
Sorry, my internet connection is not stable right now. Maybe now it's okay?
I'm hearing you.
Okay. I knew that we take Laplace transforms of the derivatives by just putting an s in front of the...
There is an assumption there. Do you remember the assumption?
The initial condition is 0.
Yes.
Right? So we're assuming that here, right?
Yes, that's correct. So you remember that transfer function representation always has the zero initial condition assumption. Okay, otherwise you have initial condition terms and you cannot write the output in terms of the input as an algebraic equation in the Laplace domain. Okay.
The reason we assume the initial conditions are 0 is just because to model the system and see how it's stable, how should we control the parameters, or is it something else?
Well, you know that every method has its assumptions. Well, the transfer function representation has that assumption. It doesn't mean that you can only use the transfer functions and block diagrams to model this system. For example, you guys have I don't know why my screen sharing has just dropped, but basically you have other tools such as state space, and state space representation does not make any initial condition assumption. Okay, so you can have for example state space representation of a system and you can handle any initial condition phenomenon, but when you derive the block diagram or the transfer function representation, you assume that you start the system initially at rest and everything starts with you applying an input to the system. Okay, so that's the drawback or the limitation of that particular modeling tool.
But still this gives us the insight how the system will behave, right?
Obviously, because if you remember, we characterize systems often with their step responses or ramp responses or parabolic responses, right? All of these inputs initially start at 0 and they assume that the system is initially at rest. So you apply a test signal, you might call it, like a step input, and the response will give you quite a bit of insight about what's going to happen with the system. And you know something else as well. Can you tell me about the system? The system is linear, remember.
I can't think of anything.
Okay, so you can also analyze the system in terms of its response to the initial condition, but provided that you assume now the input is 0. Okay, so in that case you will probably get a different transfer function in response to the initial condition. Okay, But uh, that might be a bit tricky because you can have multiple states, so it depends on the order of the system. So you might have initial conditions for each one of the states, so you can try to analyze the response to the system to each one of the initial states, and so on and so forth. So that becomes quite kind of tedious. That's why you move on to state space representation in that case. Okay. Let me share my screen again. I don't know why it just dropped. Uh, Here we go. Is there any other questions at this point? Okay, so let me continue, okay, with this. Now we are at, let's call it 5. In fact, we already called it 5, I guess, which is the end effector. So the very end point of the solenoid, okay? So what happens is that we want to basically model what's happening with the flow in response to the position of the valve needle, okay? And that's we're gonna model very simply, okay? So let's say that's the valve in turn, or let me do it this way. The valve position X in turn controls the flow of steam in the pipe. Okay? And we are going to model this as a linear relationship. We will say that the flow is linearly proportional to the position X. Okay? That's again, you might argue whether this is a very exact model. Probably not. But for our purposes right now, it's a reasonable assumption. Okay? So depending on where is the needle position in the valve, the flow will be restricted, and that's going to be related linearly with the position of the valve. So that's another equation that we have. Okay? Finally, we want to know how the flow of steam through the tank is actually affecting the temperature in the tank. So that's going to be our final model. That's going to be our item 6. Okay. The temperature in the tank first of all, it's homogeneous because it's being mixed. So we are not really dealing about how the temperature propagates within the tank. In fact, that makes that kind of complication would make the system not a lumped parameter model, but as we will see in the future, a distributed parameter model, because there will be a propagation within the system. Okay, but for the time being, we say the temperature in the tank is related with the steam flow with I will call it a first order dynamics. Let's say filling a capacitor through a resistor. So this is consistent with physical observations. So if you have a heat source within a well mixed kind of fluid, what's going to happen is that this heat input will be propagated within the tank, and because it's being mixed, it's going to be everywhere the same temperature, but the temperature will be rising with a first order response. So we expect something like this. There will be a T final, okay, and essentially the temperature will start from an initial value and it's going to be stabilizing at a final value. Okay, and the way to model that is that the equation will be the temperature. I'm going to write this directly in the Laplace domain. So the temperature in the tank will be a first order response, right? It's going to be a k theta. Sorry, let me write it this way. Okay, so it's going to be a gain, okay, let's call this k theta over tau s plus 1. Tau is the, let's say, temperature time constant. Times, obviously, the input, which is Q of S. This is steam flow. Okay, so it's a very simple model, and you know, is it the only model that can be developed? Obviously not, but I guess it serves our purposes for now. So from this, I want to basically develop. In fact, I have already developed the block diagram model. Okay, so let's mark the output of this system at the end. Theta of S is the output. What is the input to this system? Can somebody tell me what's going to be the input to this system? What's the variable that is our input?
Voltage R.
Yes, right. The reference voltage R is our input here. So R, this is the reference voltage. Okay, so let's start from the output and follow the signal as we have followed it through our equations. So we start with the output. What happens is that the output goes into a block that is a simple amplifier, which brings us to the signal B. The signal B goes towards the input, okay, and B goes. So we have R of S here, right, in the Laplace domain. We have our comparator here, plus minus. We subtract from R signal B, and let me again use Laplace notation here, B of S. What is the difference? The difference is our error signal E of S. E of S goes through an amplifier Ka. In fact, this is our controller, which brings us to voltage V of S, right? Voltage gets transformed into the current. So we have 1 over SL plus R, the electrical part of our model. So this gives us IS of S. The current goes through the motor constant Ks, which brings us to the force Fs. The force goes through the mechanical system model, the second order model that gives us the position of the valve, right? 1 over ms square plus bs plus k. That gives us the position x of s. The position results in flow through kq. This gives us the flow q of s. Sorry, let me kind of fix this part. Okay. Okay, so this is our theta of S, and here we go, theta of S. So Q of S goes to the tank or the actually the plant model. Okay, so this is K theta over tau S plus 1, and therefore the flow is transformed into the temperature uh, completing the loop. Okay. Okay. So you see that in fact we kind of picked a certain variable, an obvious variable like the output, and we started one by one. Since this is overall a single loop feedback control system, we can see that from the initial diagram. So a logical thing to do is start from, let's say, the output variable and gradually write each one of the components and process and subsystem equations, so that we move from one variable to the next until we complete the loop and we have all the components, all the subsystems in the model. Okay. So obviously this is a detailed block diagram. It shows all the physical components, like for example, let me label some of them here. Okay, so we have, for example, the controller here. So we have, basically electrical parts, valve 1, valve 2, valve 3 here. Okay, so this is like an actuator. So, and we have basically the flow component, and we have basically the plant model. Obviously, you can argue what is entirely the plant model. For example, this whole thing can be the plant model. Okay? Or you can just say, basically what, and finally, this part is basically the sensor, right? So we have the entire thing in our hand. Okay? Now the selection of the plant, really, mathematically speaking, you can combine. If you remember, if you have a block diagram, you can simplify the block diagram any way you want. You can combine any blocks into a bigger block and so on. So mathematically speaking, every block in this block diagram is the same. But physically, what we call a plant or process is essentially the parts of the system that are given to you to be controlled initially is what we call the plant. Whatever is already there. Okay? But if we, for example, select a valve and add it to the system, that is something we part of our design. So that is really an actuator. Okay? Something that's going to drive the plant, but is of our own choosing. Okay, so that we can call it an actuator. Okay, or somebody might tell you, okay, the actuator is already part of the plant. Okay, you need to supply the voltage to this existing device. So in that case, the actuator might become part of the plant. Okay, so these boundaries are not clear cut. But when things that we add to the system, an actuator is something that usually we add to the system. A sensor is usually something that we add to the system as an engineer. The controller, the comparator are often, almost always, things that we add to the system in order to change the behavior. Does that make sense?
Yes, thank you.
Okay.